The next thing that I need to introduce you before we can move to the algorithm, you can see we're doing a lot of introduction, but this, I promise, is the last one. We need to talk about policy, okay? So what is policy? Policy is an optimal action that you can take in a state, okay? So you can say policy, and I will put a star here, which means an optimal policy. For every state, it would tell me which action should I be taking. And the idea here is that you want to maximize expected reward. Because whenever you're taking the actions and you're taking the whole sequence of action, you actually don't know which reward you're exactly going to get, because you remember the world is not deterministic, you have intention to move forward, maybe you're going to move sideways and so on. But the idea here that we want in every state to select an action which optimize the expected, maximize expected utility. This is our goal. This is called policy, okay? And now let's go back to our original examples that we have over here and try to come up with different policies. And what I want to say here, that policy would very much depend on the structure of your reward. Let's say in this example, I still have +1 for this state and -1 for this state. But in addition, for every transition that you take, each time when you take an action, you're going to be paying some small price. Let's say you're going to be paying -0.001. Okay? So let's imagine how the policy, I would obviously kind of unofficially do the computation, but roughly speaking, the policy in this case is maybe gonna go this way. Okay, this is one policy that we would expect, you know, we will try to get as soon as possible to +1, and at the same time try not to go directly and encounter this penalty. Now let me and this was the case of our living reward being equal very, very small negative number. Now imagine that my living reward will be really atrocious. Let's say I would assume that I have to pay -10 for every step I am taking. If I am paying -10 for every step, this will not be a good policy, because while I'm going from here to here, I'm encountering huge penalty. So in this case, you may want to directly jump here, correct? Because you don't want to go around. And in every single place, the only thing that you're going to be optimizing is how shall I get in the smallest number of steps to this +1. So you can see, depending how we would define reward, we would have different policies. But the point that I want again to emphasize to you, notice here, let's say you're looking now at the blue policy, okay? When we're thinking about the blue policy, at every step, independently of how did I arrive to this step, I have the same one action that I am taking. And if we would have went with a finite horizon, we could not have done it. It will depend where we are in our journey, which time step. Here it's independent. Each time when you arrive to your state, your policy would tell you where to go. That's when we are talking about solving MDPs. When we're talking about it, we're talking about finding the policies. That's what it means to solve MDPs, to find the best way how to act in the world to maximize expected reward. Okay? So now we finished talking about MDPs, and the last thing that I want to say before we move forward is just to connect it to the reinforcement learning story. So here, you see, when we're talking about MDPs, you're thinking, is it the same as reinforcement learning? So in principle, the general idea of thinking is the same. The only difference will be related to the fact that when you have a reinforcement learning problem, you're not provide it with a transition function and with a reward function until you actually go in the world, experience and collect it. So we will see that a lot of machineries that we will develop today when we are talking in Markov decision processes would help us to think about reinforcement learning problems. But again, for today, we assume that all of those are given and we need to solve it, meaning to find the optimal policy for our MDP. Okay, so now I will start talking to you about Bellman equations and introduce you a tiny bit more notations related to these Bellman equations. Before we go into notations, and it's like there's so many of them, we are gonna intuitively understand where are we deriving, okay? So what is the intuition here? You need somehow to have a mechanism to propagate your reward. So let's just for now assume that the living reward is 0, that you have here +1 and -1, to make it very simple. You know this is a great place to be, correct? Because you are really getting a reward. You know that this one is also a great place to be because you are just one before the reward and there is nothing bad that can happen. So this is maybe not as good as this one, but kind of really great space to be in. This one maybe not, you know, the greatest space because you still need to traverse it until you're getting there. So we need to provide our agent with some quantification is how good is the state, what is the value of the state so that it can orient itself. Even though my reward is coming many steps ahead, I know that this is kind of a promising way to continue. So that's why we need to introduce some notion that will remember for each state what is the value of the state, how good this value is. And what the Bellman equations do, they actually connect this notion of this value of the state and the notion of policy.